Dear students, continuing our lecture series on organic reaction mechanism. This is our 26th lecture on ORM, and in this tutorial we will discuss about some problems regarding kinetic and thermodynamic control in terms of how endo and exo products they are related to kinetic or thermodynamic control. So some typical problems regarding kinetic thermodynamic control and their relationship with oxo and endo product formation will be discussed during this tutorial. So first example is the endo products, they are more sterically hindered, but still they are favored products in case of Diels-Alder reaction. Why this happens? The answer lies again in the kinetic and thermodynamic stability of the transition states which are formed during these reactions. For example, if we take cyclopentadiene as the diene, and this black anhydride will be acting as a dienophile, then we will get this type of Diels-Alder adduct formed, which may either be endo product or it may be exo product, and these are formed in 4:1 ratio, the endo product being formed in a major as a major product, although this is more sterically hindered. The basic mechanism of this product formation lies in the orbital interactions of the HOMO, that is highest occupied molecular orbital of the diene and lowest unoccupied molecular orbital of the dienophile. So these HOMO-LUMO interactions they are basically responsible for the formation of endo or exo products. Now for example, if we are having this as the diene and this as the dienophile, then the orbital interaction of these two different transition state, endo transition state and exo transition state, when these were studied, it was found that the endo transition state is such that lactone withdrawing groups points towards the two carbon atoms that will eventually comprise the C2C3 alkene. So basically what happens is that these 1,2 bond is going to react with this carbon 6, and this bond is going to react at carbon 5, and a new bond is to be formed at carbon 2 and 3, as you can see over here. Now in this case, these electron withdrawing groups which are there, they are pointing towards these carbon atoms, whereas in case of exo transition state, the electron withdrawing groups they point away from the these electron withdrawing groups they point away from the 2,3 carbon of the alkene, which is going to be formed during the reaction. So basically because of this reason, the endo transition state has lower activation energy as compared to the exo transition state. Now if we study this reaction in terms of kinetic and thermodynamic control, the aspect can be explained in terms of endo product formation or exo product formation on that basis also. So if we study the reaction coordinate diagram for kinetic versus thermodynamic control, we know at low temperature in case of Diels-Alder reaction, the reaction is irreversible and products with the lowest energy transition states they are obtained, that is known as kinetic control. Whereas where reactions they are reversible, that is at high temperature, the product mixture reflected the difference in the heat of formation or energy between the two products, that is thermodynamic control. For example, if we take the previous case only, cyclopentadiene reacts with maleic anhydride, and we study the transition states for both exo transition state as well as endo transition state for the formation of endo product or exo product. Now if you see the transition state for the endo product, this red one is the energy profile diagram for the endo product. So these are the reactants. A is reactant cyclopentadiene and maleic anhydride, and formation of product at D, that is this product, endo product, passes through this transition state which is the endo transition state at point C. And if we compare the endo and exo transition state, this exo transition state is this one B. If we compare the energy of these two, endo product is at lower energy than that of exo product, meaning that means this product will be formed faster because this is having a low activation energy. So therefore at low temperatures, when temperature is low, the reaction will try to go through this mode, that is endo transition state. So at low temperature, forward reaction will be through endo transition state, that means A, C and D. So A changes into endo transition state, and which ultimately gives us endo product D. And at low temperature reverse cannot take place, that this endo product formed through this transition state gives back us this starting material. Therefore this reaction mixture will reflect the differences in energy between B and C. So if at low temperature is low enough that we cannot achieve this B, then only endo product will be formed, and this is what known as kinetic control. Endo product is not the more stable product. More stable product is exo product because of the energy difference between the reactant and the product. Here endo product is less stable as compared to exo product, but because at low temperature the activation energy to form this exo transition state cannot be achieved, therefore the reaction will follow ACD path, that is endo transition state will be formed. But when the temperature is high, so when temperature is high, then reverse reaction is also accessible. So that means when temperature is high, then this can go back to these, and then it can achieve the exo transition state, and it can give us a most stable product, which is thermodynamic control product, that is exo product can be formed. So this is how, on the basis of this energy level diagram, we can differentiate that whether kinetic control product will be formed or thermodynamic control product will be formed, and that is how we get endo product at low temperatures in case of Diels-Alder reaction, and exo product or a mixture of endo and exo product at higher temperature, because then reversible reaction can also take place, and we can have a mixture of endo and exo products. So in conclusion, that means Diels-Alder is normally run under condition where reaction is irreversible. So that means when reaction is irreversible, endo transition state, which is at lower in energy than the exo transition state, that will be followed, and endo products, they will dominate at low temperature, and this is called as kinetic stability. And similarly at high temperature, as I have told you, that reaction is reversible in nature and more of the exo product form will be there due to thermodynamic stability. So this is how we can differentiate that how kinetic stability and thermodynamic stability lead to the formation of endo or exo products in Diels-Alder reaction. We can take one more example. The cyclopentadiene, we know this slowly undergoes a Diels-Alder reaction with one more molecule of cyclopentadiene to give us dicyclopentadiene. And when temperature becomes high of the order of 180 degree or 200 degree centigrade, then this can be again degraded or to give us the reactant, or this is called as retro Diels-Alder reaction. Now at low temperature, as we know, only forward reaction will take place, and we can have either endo product or exo product depending upon the transition state of endo and exo products. That if at that low temperature we can achieve only the activation energy which can lead to the formation of endo product, then only endo product will be formed. But if we can achieve the formation of exo only, then a mixture of endo and exo, they will be formed. So for example, this can again be explained on the basis of energy profile diagram. So as you know, ACD is the energy profile for the formation of endo product, and ABE is the energy profile diagram for formation of exo product when two molecules of cyclopentadiene, they undergo Diels-Alder reaction to give us dicyclopentadiene. And here also at same thing which I have explained in the previous example, the endo transition state is lower in energy than the exo transition state. Therefore endo products, they will be dominant at low temperature. So that is why when at low temperature the two molecules, they combine, we get only one product, that is endo product. But at high temperatures, when the reaction is reversible, more of exo product is also formed due to the greater thermodynamic stability of the reaction. So when this reaction was actually performed at 23 degree centigrade, it gave only endo product. Whereas when a solution of cyclo was heated at 200 degree centigrade, then endo to exo product formation ratio was 4:1. So because at 200 degree centigrade the reaction is reversible in nature, whereas at 23 degree centigrade the reaction will be irreversible in nature and only endo product will be formed. Then the geometry of Z and E enolates formed during Aldol reaction depends on reaction conditions and nature of the substituent, and these reaction conditions also lead to the formation of kinetic enolates or thermodynamic enolates. For example, if we are using a strong base at low temperature and our reaction time is a short reaction time, then a kinetic enolate will be formed. But if we are using a weak base like sodium hydroxide or potassium hydroxide at high temperature and the reaction is performed on a longer period of time, then a thermodynamic enolate will be formed. So for example, if say we are having this type of carbonyl compound and it reacts with base, any of these, either strong base or weak base, then kinetic and thermodynamic enolates, they are formed depending upon whether we are using a strong base or a weak base. So when a strong base is used, in the first instance we will get this type of kinetic enolate, and then this kinetic enolate will abstract this alpha hydrogen from another molecule of the carbonyl compound to give us a more stable thermodynamic enolate. Now, because of the kinetic and thermodynamic stability, when aldol condensation is done, then either there is a syn addition or anti addition of one carbonyl molecule to the other carbonyl molecule, and this leads to the formation of diastereomer, and that how much of these syn or anti diastereomers they are formed, this depends on reaction conditions and nature of the substituent. And this again, as you have seen in the previous slide, the reaction condition and nature of substituent means that whether the reaction is controlled by kinetic control or this is under thermodynamic control. So for example, if the reaction is under thermodynamic control, then Z and E forms of enolates, they are in rapid equilibrium. So you can see over here, so this is our Z enolate and this is our E enolate, and reaction is under thermodynamic control, and in such circumstances the product distribution is dependent on the relative stability of these 6 membered chair shaped cyclic transition states, and likewise we will get either syn product or anti product. Now if you see the these cyclic transition states closely, the syn product has been formed where the R1, this one, is axial in nature, whereas R is equatorial in nature. So when this group is axial in position, then this transition state is less stable. So when both of these they are in equatorial position, this cyclic transition state is more stable, then it will lead to the formation of anti-product. And because this is more stable transition state, the energy of the system through which this will lead to the formation of product, that is anti-product, this will be formed as major product because this will be lower in energy, because here the transition state leading to the formation of this product is lower in energy. So that is why we will get a major anti-product under thermodynamic control. Now under kinetic control, the Z and E enolates, they are formed rapidly, but they are formed irreversibly, and the relative amount of syn or anti enantiomers or diastereomers formed will determine the product distribution. For example, if we take this 2,2-dimethyl-pentane 3-one or 2-methyl-pentane 3-one, these are two different ketones, but the only point of difference is here we are having 3 methyl groups attached to this carbonyl, whereas here we are having only 2 methyl groups attached to the carbonyl. So this is tertiary butyl group and this is isopropyl group, right? And because of rest of the conditions and other substrates, they are same. The base which we are using LDA is also same. When this group is a tertiary butyl group, then the product formed is more than 98% syn product is formed. Whereas if this is the substrate where the group attached is isopropyl, then syn to antiproduct, they are formed in 4:1, and only reason for this is that the reaction is controlled kinetically, and because the formation of Z and E enolates is irreversible, then once the amount of Z or E enolates they are formed, they are not going to be converted into either Z cannot be converted into E or E cannot be converted into Z. So therefore, if we consider these two examples, in the first one the Z enolate is normally formed, which will give us only syn diastereomer as the major product. But when this is formed as a substrate, both Z and E enolates, they are formed in 4:1 ratio. That is why we are getting this product in 4:1 ratio. And thank you very much.